Hello everyone. Welcome to Design Hub, Heavy Machinery. In this video, we will explore how an excavator knows its bucket position in three-dimensional space, how this enables bucket automation, and how artificial intelligence makes this control smarter and smoother. In a traditional excavator, the operator moves the joystick, hydraulic oil flows to the cylinders, and the bucket moves. The machine itself does not know where the bucket is. Everything depends on the operator's eyes and experience. While this works, accuracy depends heavily on skill, visibility, and working conditions. When forward kinematics is introduced, this changes completely. Sensors continuously measure how much the boom, arm, bucket, and upper structure are moving. Angle sensors capture joint motion in real time, while the excavator already knows its own geometry, such as the length of the boom, arm, and bucket linkage. This geometric information comes from the machine design and does not change during operation. All this data is sent to the excavator's control computer in numerical form. Joint movements are stored as angle values, link lengths are stored as fixed parameters, and reference points like the bucket tip are clearly defined in the system. Using this information, the control software applies forward kinematics to calculate the exact three-dimensional position of the bucket tip. In simple words, the machine converts joint motion into an X, Y, and Z position in space. This calculation runs continuously while the machine is working. First, the excavator calculates the bucket position in a vertical plane. The horizontal reach of the bucket is calculated as R equals L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2 plus L3 cosine theta 1 plus theta 2 plus theta 3. The vertical height of the bucket is calculated as Z equals L1 sine theta 1 plus L2 sine theta 1 plus theta 2 plus L3 sine theta 1 plus theta 2 plus theta 3. Here, L1, L2, and L3 are the lengths of the boom, arm, and bucket, and the thetas represent the joint angles. Next, the swing motion is included to convert this into full three-dimensional space. X equals R cosine theta S. Y equals R sine theta S. Z remains the same. Now the bucket position is known exactly as X, Y, and Z coordinates. Once the bucket position is known, automation becomes possible. The excavator is given digital targets such as a required digging depth, a flat ground level, a slope, or a safety limit. These targets are stored as numbers or simple geometric surfaces inside the control system. The software continuously compares the live bucket position with these targets and calculates how far the bucket is from where it should be. For example, the depth error is calculated as error equals current bucket height minus target depth. This tells the system exactly how close the bucket is to the desired result. This position information is then used to control the hydraulics more intelligently. Instead of moving cylinders blindly based only on joystick input, the excavator adjusts hydraulic oil flow based on position error. As the bucket approaches the target, the error becomes smaller, and cylinder speed is automatically reduced. If the bucket reaches the target or a safety limit, further movement in that direction is restricted. The operator may continue moving the joystick, but the machine will not allow incorrect motion. The most important point is that this automation does not rely on complex robot behavior. The system does not try to calculate perfect joint positions. It simply observes where the bucket actually is and reacts to that position. Because of this, the automation remains reliable even when loads change, structures flex, and hydraulic behavior is not ideal. In modern excavator automation systems, sensor data is not processed using long formulas. Instead, it is handled using matrices. Automation software works best with structured numerical data that can be updated quickly. Joint angle values are placed into transformation matrices, along with link lengths. These matrices contain the same sine and cosine terms found in formulas, but they keep rotation and position together in a compact and efficient form. As the excavator moves, only the angle values inside the matrices change, while the matrix structure remains the same. The software multiplies these matrices together to form one final matrix that represents the full excavator attachment. From this matrix, the bucket tip position is directly read as X, Y, and Z coordinates. In effect, the familiar kinematic formulas are automatically generated inside the matrix calculations, without being written out explicitly. By using matrices instead of formulas, the bucket automation system can process sensor data hundreds of times per second, compare bucket position with digital targets, and smoothly adjust hydraulic motion in real time. Before we conclude, let us briefly look at reverse kinematics. Reverse kinematics answers a different question. What joint angles are needed to reach a desired bucket position in space? Instead of calculating where the bucket is, it starts with the target position and works backward to estimate joint movements. Reverse kinematics is used in excavators mainly in special cases, such as research machines, autonomous digging prototypes, and simulation or offline planning. It is also common in robotic arms and electric machines, where actuators can precisely follow calculated joint angles. Even in these cases, reverse kinematics is usually applied only at a high planning level. The actual machine motion is still tracked using forward kinematics feedback, and reverse kinematics does not directly control hydraulic valves. In simple terms, bucket automation may look like magic from the outside, but inside the machine it is built on clear geometry, real-time sensing, and smart control logic. This is how modern excavators become smarter, safer, and more productive using basic kinematics and real-time data. AI adds an additional control and intelligence layer on top of kinematics-based positioning. While kinematics provides an exact geometric bucket position, real job site conditions introduce uncertainties that pure geometry cannot model. Soil stiffness varies continuously, bucket loads change during digging, hydraulic response is nonlinear, and system behavior shifts with oil temperature, component wear, and pressure losses. AI models learn these effects directly from operational data and predict how the excavator will actually respond to a given control input under current conditions. Using machine learning models, the system estimates dynamic behavior such as joint velocity response, hydraulic delays, and load-dependent motion resistance. This allows the controller to compensate for lag, overshoot, and oscillations before they occur, resulting in smoother bucket motion and more stable control. Instead of reacting only after an error appears, AI enables predictive adjustment of hydraulic flow and timing, improving both accuracy and machine feel. AI also enhances bucket position accuracy through sensor fusion. Forward kinematics provides a position estimate based on joint angles, but this estimate can drift due to sensor noise, joint clearance, and structural deflection. AI combines joint angle data with hydraulic pressure sensors, inertial measurement units, GNSS positioning, and, in some systems, camera or lidar inputs. By weighting and filtering these signals intelligently, the system reduces noise, corrects drift, and maintains reliable bucket positioning even in rough terrain and low visibility conditions. At a higher level, AI analyzes repeated digging cycles to identify efficient motion patterns. It can recognize optimal entry angles, lift trajectories, and dump motions that minimize energy loss and cycle time. The system then assists the operator in reproducing these patterns, reducing fuel consumption, mechanical stress, and operator workload. Importantly, this assistance remains adaptive and non-intrusive, preserving operator control while enhancing performance. In technical terms, kinematics provides the deterministic geometric state of the machine, while AI models the uncertain dynamics and environment-dependent behavior. Together, they form a hybrid control system that is precise, adaptive, and robust. This combination is driving excavators away from purely manual operation toward intelligent, semi-autonomous machines capable of consistent performance in complex real-world conditions.